Okay, so today we're going to prove by the principle of mathematical induction that for every n contained in the natural numbers, x minus y divides x to the n minus y to the n. So let's go ahead and start the proof. So for PMI, we have to first establish a base step, okay? So we just want to determine if we plug in 1 for n, if x minus y will divide x to the 1 minus y to the 1. So S of 1 states that x minus y divides x to the 1 minus y to the 1. And of course, x minus y divides itself, so that checks out. Let's go ahead and do one more. Let's look at S of 2. We know that S of 2 would state that x minus y divides x squared minus y squared. Well, we know that x squared minus y squared is equal to x plus y times x minus y. And of course, x minus y divides x minus y times something. So this implies, right, that S of 2, which is x minus y divides x squared minus y squared, is true, right? So that checks. So now let's go ahead and move on to the inductive step. So remember, with the inductive step, we're going to assume S of k, which states x minus y divides x to the k minus y to the k, is true, right? Is true for some k contained in the natural numbers. So remember, with induction, or for a principle of mathematical induction, we want to show, right, that S of k plus 1 is true, where assuming that S of k is true, right? So we want to show that S of k plus 1, where, let's see, x minus y divides x to the k plus 1 minus y to the k plus 1, right? We want to show this, assuming this, okay? So let's go ahead and consider x to the k plus 1 minus y to the k plus 1. We know that this is equal to, so this is equal to x times x to the k minus y times y to the k. So the next part is a little trick. We can do this, x times x to the k minus y times x to the k plus y times x to the k minus y times y to the k. Okay, so notice how I subtracted y times x to the k and I've added y times x to the k. So this line is the same as this line, but there was a purpose for that. Okay, because now what I have is I have that I can factor out x to the k here. So x to the k times x minus y plus, and I can factor out a y here. Y times x to the k minus y to the k. And this is what I have here. I have, of course, x minus y divides itself, right? And from the assumption, I know that x minus y divides x to the k minus y to the k, right? So this implies that x minus y divides x to the k times x minus y plus y times x to the k minus y to the k, right? I know that x minus y divides this because by assumption, x minus y divides x minus y, and x minus y by assumption divides x to the k minus y to the k, right? So this means x minus y divides this sum, and we know that this sum is equal to x to the k plus 1 minus y to the k plus 1. So we've shown that assuming that x minus y divides x to the k minus y to the k, we can show that x minus y divides the next one, right? It divides x to the k plus 1 minus y to the k plus 1, and that is what we set out to do. So by PMI, we know that for every n contained in the natural numbers, that x minus y divides x to the k, or x to the n minus y to the n. And that is our proof.